What you just saw was an example of a Mandelbrot set, or a particular set of complex numbers that have fractals, or infinitely repeating shapes, when plotted on a graph. Such a concept is pretty hard to understand. However, by the end of the video, you'll go from this to this. Let's get started. First discovered by Benoit Mandelbrot around 1975, fractals were described as geometric shapes that, when divided into parts, would be a smaller replica of the whole shape. The concept of fractals have been around in earlier times, but it is Mandelbrot who first put this mathematical trend into words, describing these fascinating shapes. The term fractal was taken from the Greek word fractus, meaning broken or fracture. However, there's more to that than just imagining pieces of a puzzle. Let's start off with the basics. In order to understand what makes a fractal, we have to think about it mathematically. We first start with a complex plane based off of the equation a plus bi, where I is the square root of -1. From this grid, we can see that every distinct combination of coordinates a and b create a line. From this line, we can determine distance using its absolute value. Visualizing a Mandelbrot set through this method makes it a lot easier to interpret some of these wildly colored images. To get to the Mandelbrot shape, we start with the equation f sub c of z is equal to z squared plus c. C represents whatever complex number assigned to it, as seen in the grid before, while z represents an input. Through this process, we first assign a value z, where we then obtain the value f sub c of z. When f sub c of z is obtained, it gets plugged back into the equation as z again. This process is repeated an infinite number of times, where its trend can be observed with two outcomes. Outcome 1 is that the number gets infinitely large very quickly after the first few repetitions. Outcome 2 is that the number is actually bounded and repeats back and forth and never gets larger than the value of 2. Let's see some examples of both. For example, let's try f of 2. When z equals 0, f sub 2 of 0 is equal to 0 squared plus 2, which is equal to 2. Then we repeat this process again by placing 2 back into the equation as z. Then we see f sub of 2 is equal to 2 squared plus 2, which is equal to 4 plus 2, which is equal to 6. This step is repeated an infinite number of times, and as you can see, it reaches all the way up to infinity. As we see in this trend, the z value increases very quickly after the first few iterations, which is outcome 1. Now let's try f sub of -1. When z equals 0, f sub -1 of 0 is equal to 0 squared minus 1, which is equal to -1. Then we repeat this process again, placing -1 back into the equation as z. Then f sub -1 of -1 is equal to -1 squared minus 1. As we can see, 1 minus 1 is equal to 0. When we plug the value of z equals 0 back into the equation, we can see that repeating this equation gives us a pattern of 0 and -1, never growing larger than specified, which is outcome 2. Let's bring this together. So, when comparing various complex numbers to the equation, there are a certain range of values in which outcome 2 is true, and a certain range of values where outcome 1 is true. The set of numbers that are outcome 2 are more specifically known as the Mandelbrot set. The combination of these outcomes are how such colorful pictures are generated. Those complex numbers where the iterations are bounded, outcome 2, are portrayed as black. The infinitely expanding iterations, outcome 1, are given another color depending on how long it takes to get to infinity. However, at the edges between outcome 1 and outcome 2, it is impossible to tell where the boundary is. If the value of c, or the complex number, is changed by an infinitely small amount, the outcome, whether 1 or 2, might change due to this very small amount. That is why when we try to zoom in, we get another variety of outcomes and another new shape. We see fractals all around us and their strikingly repetitive characteristics. A cloud is composed of smaller clouds that are very similar, that looks alike. A pine tree is made of branches which are made of smaller sticks. All around us, we can see that nature is composed of these beautiful fractal shapes. Not only do fractals apply to nature, but they also have useful societal applications as well, such as in computer graphics, in computer file compression systems, in the architecture of the internet, and even in diagnosing diseases. Even in today's society, we are still finding fields where fractals both provide beauty and application to people globally. Look around you, and you might be surprised at what you find as well. Thanks for watching.